In this video, we have a complicated resistor network that isn't series or parallel. We've labeled the branch currents I1 through I6, and we're going to set up a system of 6 equations and 6 unknowns to solve for the branch currents. We're going to plug those equations into a computer algebra system, and it turns out there's an internal dependency hiding in our original set of equations, and we're forced to correct for that by adding a 7th equation before we can nail down the branch currents. Finally, we're going to compute the voltage drop over the 5 ohm resistor. So just a quick comment on why these are not in series or parallel. When two resistors are in series, they're guaranteed to always have the same current through them. But I can see with all the nodes in this resistor network, all the ways that current is allowed to split and merge, I'm not guaranteed to have the same current through any two resistors. Likewise, none of the resistors are in parallel. If you're tempted to say the 2 ohm and the 1 ohm are in parallel, that's not right because their high ends are separated by a resistor with a current flowing through it. So they're not guaranteed to have the same potential at the top, and therefore they're not guaranteed to have the same potential difference across them, which is what we mean by parallel resistors. So we attack this problem by using Kirchoff's laws, and I'll post a link real quick to the video where I introduced Kirchoff's laws. And there's just two basic ideas there. One, the total current flowing into any node must vanish. It must be 0. In other words, current in equals current out. So we have 4 nodes to choose from here, and we can apply that first Kirchoff law to each of those 4 nodes. So I'm going to start with the one on the left and work my way to the right. And at that leftmost node, I6 is flowing into that, and I1 and I2 are flowing out of that. So I6 is equal to I1 plus I2. At the upper node in the resistor network, I1 is flowing into that, and I4 and I3 are flowing out of it. At the lower node in the resistor network, I3 and I2 are flowing into that, and I5 is flowing out of that. And finally, at the rightmost node, I4 and I5 are flowing into that, and I6 is flowing out of it. So there's our first 4 equations, and then we use Kirchoff's second law. And the idea here is that the sum of the voltage changes around any closed loop in a circuit must vanish because you get back to the same original voltage by the time you complete the loop. So we have to choose which complete loops we're going to use here. And I just wanted to point out that our first 4 equations covered all of the resistors, but I don't have any equation that involves the power source yet. You better have one at some point. And so what I'm going to do is choose loops that include the power source. I'm going to start from the lower left corner here. And in my first loop, I'm going to go up to the resistor network and cross over through the upper branch of the resistor network, and then I'll get back to my starting point. In my second loop, I'll use the lower branch instead. So as I go up the power source, that's a voltage change of plus 5. And then as I go down over this 2 ohm resistor, that's a voltage drop of V equals IR, which is 2 times the current I1, so minus 2 I1. And then I have a voltage drop again over a 2 ohm resistor with a current of I4. So IR is 2 times I4. And there's no other circuit elements to pass through before I get to my finishing point. So equals 0. The sum of the voltage changes equals 0. All right, then I pass through the lower branch instead. So I have 5 volts minus I2 times 3 ohms. I can call that 3I2. Minus I5 times 1 ohm, that's minus I5, equals 0. Now when we're dealing with a system of 6 equations and 6 unknowns, doing this by hand is unreasonable, and I'm going to use a computer algebra system for this. So here we are in wxMaxima, and I've input all my equations. Notice that I assign the names of the equations using a colon. And also notice that in cases where I have to multiply 2 things in Maxima, I must use the multiply symbol. You can't just write them next to each other. So that's Shift 8 for an asterisk, and it will make that dot. Putting a semicolon at the end of each of these lines and pressing return to give me line breaks makes it so when I hit Shift Enter to assign all these equations to their names, Maxima will repeat those equations to me so I can check my work and make sure it's what I meant to type. Then I'm going to get into solving the system. So this is how the solve command works for a system of equations. I just put my list of equations in brackets, the list of variables that I want to solve for in brackets, and when I hit Shift Enter, it will give me the solutions. Now Maxima tries to do everything in exact fractional form, and I would prefer to have decimals here, so I'm going to put float out in front. and then I hit Shift Enter. And notice what Maxima says. Dependent equations were eliminated. That means there's some way of combining two or more of our original equations to obtain another one of them. In other words, we don't have enough independent equations in our system to actually solve for each of these currents. So when I go back to my equations, I suspect here that the dependency is lurking in my current equations because I've described how I6 splits up into pieces, but then I've described how I6 is obtained by putting those pieces back together. So I just want to illustrate real quick where the dependency actually is. If I take my original equation, I6 equals I1 plus I2, and then I use my second equation, I can replace I1 with I4 plus I3. And then I take my third equation and I can replace I2 plus I3 with I5. I've just obtained a copy of my fourth equation. So that fourth equation is actually derived from the first three. Okay, we're going to need a seventh equation then, and we'll just type it into the computer algebra system. What I'm going to use for this is a loop around the left side of the resistor network. I'll start at the lower left end. The first thing I cross is the 2 ohm resistor with I1 passing through it. That's a voltage drop because I'm going the same direction as the current, so negative 2 I1. The next thing I pass through is I3 passing through a 5 ohm resistor, so that's minus 5 I3. And then be really careful about the last one here. We're crossing over this 3 ohm resistor in the opposite direction of current, which means it's a voltage increase of 3 I2 equals 0. Now we don't even have to delete that dependent equation. We just have to add another independent equation to the list. So that would be equation 7. I hit Shift Enter to assign all of my equations. And now there's 7 of them. And now I'll modify my solve command to include my 7th equation. And hit Shift Enter, and we should get decimals out of this. And I do. So there's our decimal solutions for the 6 currents that are flowing through this circuit. These would also allow you to determine the voltage at any node that you wanted in the circuit. But the one follow-up question that we're asked here is to find the voltage drop over the 5 ohm resistor. So it's just a 5 ohm resistor with a current of I3 flowing through it. I'll label the node on the high side of that resistor as A and the low side as B. And I can find VAB just by using Ohm's law. V equals IR, and I3 is 0.185 amps. And my resistance is 5 ohms. And I end up with a voltage drop of 0.925 volts over that particular resistor. If you find the physics content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce over 100 new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.